Alrighty. So I think we were looking at the first problem was computing some matrix multiplication, right? Let me just pull that aside. Yeah, some matrix multiplication. A is equal to this matrix E. Um, yeah, I guess there's nothing too much to say about these. Did you have much confusion? You said that they were pretty straightforward.
The first part, mainly the part B for the first problem,
Yeah,
was the
so
main part of confusion.
just computing these out, right? You notice that you get something like 1, 2, 3, -1, -2, and -3, right? And then 2, 4, 6. And you can already kind of tell that there's a bit of redundancy here, right? Like each of the rows feels like the other rows. Each of the columns kind of feels like the other columns. They're just off by some constant multiple, right?
Right.
So that's sort of your hints that, okay, yeah, these are probably linearly dependent. There's probably some redundancy there. And if you go ahead and do a reduced row echelon form for this, I I mean, there's not even that much to do, right? They're basically saying for part B, they're basically saying to augment this with a zero matrix, or sorry, the zero resultant, right? And then they're basically asking you to just do the reduced row echelon form, which basically just comes out to eliminating rows 2 and 3, because they're perfect multiples of each other. Does this seem reasonable so far?
Yep.
Yeah. So then,
Then you can consider those two rows to be free variables, right?
exactly right. For each one that has a leading zero instead of a leading one, let's do a free variable. Like let's call this s and let's call this t. So what the first equation is telling you is that uh, so I guess if the original ones are um shoot, what's the notation here? Is this, are we calling this like x1, x2, and x3? And then it becomes like x1 plus 2s plus 3t is equal to 0? Does that seem
Yeah.
about right?
Yeah.
So then x1 is equal to minus 2s minus 3t. And then
Yep.
your matrix of x1, x2, and x3 just becomes minus 2s minus 3t, uh, and then just s and then just t. Because x2, as we said, we basically said that x2 was s and x3 was t. And that's basically, that's basically all that's saying. Um, I guess, another way to interpret this is sort of as two separate vectors, right? This is sort of what made it make sense to me. Like one vector is minus 2s and s and 0, and then the other vector is minus 3t, 0, and t. So this is basically like some combination of um, parametric vector form, right? I think parametric vector form basically means you just pull the s out, so to speak. 1 and 0. Is this the notation that you use? Does this look
Looks.
familiar?
Yeah. 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 Yeah.
Yeah.
Yeah.
So what it's basically saying
Yeah.
is that once you sort of
It's saying
crunch
it.
through these are your two vectors, right? The -2, 1, and 0, and then -3, 0, and 1. And what this is saying is, like, if we draw this on like well, this is a bit hard to draw in 3D, but I'll try. So if you have an XYZ plane, one of your vectors looks like -2 in the x direction and 1 in the y direction. So if each of these is the positive direction, that's sort of like -2 and 1. So this is sort of like your S vector, right? Or sorry, this is sort of like the first vector, this one. And then S basically lets you scale in stretch or reflect that as you please. And then T is basically saying -3 and Z. So the other one is sort of like going upwards a little bit. But it's basically saying that you get, this spans the plane formed by these two vectors. Feeling reasonably comfortable with that?
Yes. No, no.
Yeah.
I
So
just
let me.
didn't understand what to do from the -2s minus 3t point.
Gotcha,
And then
gotcha,
you just
gotcha.
split them up. I didn't do that. That's where I got lost there.
Yeah, I think that this is what they mean by parametric vector form, because this is a parameter and this is a vector. So parametric vector form, right? Um, but
Gotcha.
what it sort of means is split it up, show that there's a vector component, like just a straight up vector, and then show how that vector gets multiplied by some parameter. And you can kind of see just from this form, you can kind of see how a plane is spanned, right? And
Yeah.
one of the things I like to sort of just as maybe to watch out for like a trick question, right? What if instead of giving you what if instead of the RREF looked like this instead? Let's say they added in a new let's say they added in a new x4, a fourth column, and it was just 0, 0, 0. And then the resulting matrice was still and sorry, the what do you call this extra part? The adjunct or the extra part? Augmentation, right? The
Yeah.
augmentation is still 0, 0, 0. What would you say about this extra variable x4? What can this be?
Anything still, right?
Yeah, exactly. Anything, right? So like st, and let's maybe call this u, right? What this math is saying is that this thing is not being multiplied at all. Like this u is being multiplied by 0, 0, 0. The column vector is 0, 0, 0, which means that this u can be anything, and it ends up not contributing to the result at all. Right? U could be a million, but the fact that it's getting multiplied by all zeros means that it just doesn't matter. So sometimes you see a kind of trick question like this, so to speak. And I think it actually comes up in one of your later problems down here. But I just want to bring this up. But okay, now instead of all zeros, let's say that one of these was 1. And let's say that this was like 5. What would you say about, what would you say now?
Only the second row would be free. So then x4 would be 4.
It would be 5. But yeah, like, yeah, x4 would just have to be the straight
Oh,
up
yeah,
value
yeah, yeah.
5.
I know.
Yeah, yeah, exactly. So what this would look like is most of this would look the same. Instead, there's an extra x4, and then there's just instead of s's and t's, you would just have an extra 5 down here, right? This 5 isn't a what do you call it? It's not being parameterized or anything like that. It's just this extra. It's just this extra piece that's being added on, so to speak, right? If you wanted to propagate this all the way through the problem, you would have to add on an extra vector. Oh, and then there would be a 0 to round out the columns. But yeah, that's how the problem would change if you added in a little bit of a twist to it. But I just wanted to sort of give you a complete picture because sometimes teachers like to throw conceptual curveballs. But yeah, are you feeling? If you're feeling good about that one, do you want to discuss the next one? Yeah,
Yes, please.
yeah. So the next one, I haven't multiplied that matrix C myself. I don't know if there's an interesting pattern. What did you get for the result for that one? If you don't have it on hand, I'll just multiply it quickly. But
I got 1.
one.
Hello? Can you hear me?
Yep, I'm there. Yep.
Okay. By rows, it's 1, 2, 3,
Mm-hmm.
-7, -2, -1,
Mm-hmm.
and then -1, 4, and 7.
Okay, so that's kind of awkward. I don't see any particular pattern here immediately. But then what did you get once you did the REF?
I didn't get that far.
Oh, you didn't get that far? Okay, that's fine.
Give me
Yeah,
1 second. I was almost done. I'm almost
sure, no worries. Uh,
unless you want to keep going.
yeah,
Probably
I mean, I
enough
feel like this
time.
is probably exactly the same as the previous problem, or I could just quickly punch it into an online calculator to find the REF. I'm just trying to figure out if there's any interesting pattern here, or if it's just more of the same.
We can do that,
Um,
yeah.
yeah, maybe let's revisit this one at the end and talk about the next conceptual ones. Yeah, gotcha. Is that cool by you? Hello, you there?
Okay. I did get it to. Hello?
Yep. Hey, you there?
Yeah,
Yeah,
sorry. Cutting out a little bit.
sure. Okay, no worries.
I got it down to the R RREF if you want it.
Sure. Yeah, let's hear it.
From rows, it's 1 0 negative 1 3 or 1/3, sorry.
Okay.
Then 0 1 5/3, and then a row of zeros.
Okay. So then, what would you say? How many free variables would you have for this?
One in the third row.
Exactly. So let's call this maybe S. And then it looks to me like, by this logic, if we're calling this x1 and this x2, we would have x1 minus 1/3 s is equal to 0, which is the same thing as x1 is equal to 1/3 s, and x2 is equal to negative 5/3. Well, I guess I'll write it out differently. x2 plus 5/3 s is equal to 0, which is the same thing as x2 is equal to minus 5/3 s. And then to just quickly turn this into a, try to find all the solutions, well, then we just rewrite x1, x2, and x3. Remember that x3 is, we're defining it as s, is equal to 1/3 s, negative 5/3 s, and just s. So that's basically 1/3, negative 5/3, and 1. That's our vector. Easy enough?
Easy enough.
Okay. Alrighty. So if we move on to the next one, it's asking us whether there exists a 3 by 2 matrix A whose columns span R3. So I think this was very similar to a question we discussed last time, right? A 3 by 2 matrix. 3
Yeah.
by 2. And remember that 2 is sort of the input space, right? It's going to be an x1 and x2. And then the output space is going to be like B1, B2, B3. So is there such a thing, right? So two columns, right? So there's going to be a V1 and a V2. And then we draw columns. This is sort of the notation for columns, just like vertical lines, right? So can two vectors, V1 and V2, span a three-dimensional space? That's the question that boils down to. What do you think? If you have a
Wait.
three-dimensional space, what's up?
So this there isn't one, or there is one?
It's a
There
true or
isn't, right?
false. It's a true or false
There is.
question, or a yes or no question. Can two vectors span a three-dimensional space?
No, right?
Correct. No. If you have n vectors, that can span at most an n-dimensional space, right? So if you only have two vectors here, if you draw any two vectors, at best you can get a plane. You can get an entire plane if the two are not redundant with each other. If they are redundant with each other, you're only getting a single line, right? But there's just no possible way two vectors is gonna let you like span more than a plane, right? You can kind of like think about the plane that it traces out. Any two combinations of any combinations of these two vectors is going to live inside that plane. And you can just sort of like mentally play around, right? It's just that there's like if you like sort of switch to your reference frame of the plane, both vectors are living inside it, and there's no way to go into or out of that plane, right? Can you picture that?
Yeah.
Yeah. So exactly. And if you want to like think about this problem in terms of the wording of the hint says, what's the shape of the RREF of A, right? They're trying to get you to think about a very similar concept, which is basically saying, hey, there's going to be at most two pivot points, right? And we know that a matrix with at most two pivot points is only going to be able to span at most two dimensions. And
Because there's
part
only two true
Yeah.
two true equations that could fit.
Yeah, I guess you could put it that way, right? The number of pivot points that you have is sort of the number of independent vectors that you have. I don't know if you've ever made that connection before, but it's sort of one of the fundamental ideas. And if we wanted to extend this concept to part B, where we're asked about more generally, we have m greater than n, and we're being asked about a m by n matrix spanning Rm. And remember, m is the larger one. For the exact same reason, there's only n vectors, and n is less than m. So there's just no way that that's going to be able to span that larger space. If you have n vectors, you're only going to be able to span up to Rn, but m is too large. Make sense?
Wait, go over that. Can you word that a
Of
little bit
course.
differently? I'm kind of
Of
lost.
course, of course. I realize that n and m sound very similar, right? So what I'm saying is, if you have an arbitrary matrix of shape m by n, where m is larger than n, that means that this matrix is taller than it is wide, right? It's taller than it is wide. This means that whatever m for Mary dimensional space that you have, right? This might be 3-dimensional, this might be 10-dimensional, right? Maybe let's use like specific numbers just to see the pattern a bit more. Let's say that m is 10 and n is 7, right? So you have 7 vectors living in a 10-dimensional space. And what I'm telling you is that 7 vectors isn't enough. You need at least 10 vectors to span a 10-dimensional space. 7 isn't going to cut it. Do you see
Oh,
that?
okay.
Yeah.
Yeah, yeah,
It's if you can boil it down to a certain point, it's just counting, right? But it's hard to visualize past 3 dimensions, so that's a
yeah. That's
little bit
pretty simple.
tough. But it's just saying that the pattern continues, right? If you have one vector that can span a 1-dimensional space, 2 vectors can span up to 2, 3 can span up to 3. But if you have n vectors and you're trying to span a space larger than n, it just can't be done, right? Every vector, every unique vector, or let's say it this way, every additional non-redundant vector can give you an extra dimension. At most one extra dimension, right? But if you're,
Wait, one more
what's up?
time. Every vector can give you one additional dimension.
Yeah, every vector can give you at most one additional dimension.
Okay, so 3 vectors, 3 dimensions, 2 vectors, 2 dimensions, so on.
Exactly, yeah. But
Okay.
7 vectors is not going to be able to get you 10 dimensions, no matter how clever you are. And when I say get you 10 dimensions, I mean spanning 10 dimensions.
Right.
Yeah. Does it feel reasonable?
Yes.
Yeah. Yeah, and it's like, again, you can play
And
around
that
with
n
this.
times n space, well, m is the dimension and n is the vectors. Is is that always true that it's m space and n vectors, or just for this particular problem?
For this particular problem, they're saying consider a linear transformation
Okay.
with n vectors and m dimensional output. So that's for this particular problem. They're doing this setup. Let me flip this around on you, okay? Let's do it the other way around. Now let's say that m is less than or equal to n, and you have a m by n setup. Is it possible that the vectors span Rm now that we've reversed the sign?
Yes.
Yes, exactly. Yes. This could be like a 3-dimensional output and maybe like a 5 vectors, right? And what that's saying is, okay, if this is R3 and we have a three-dimensional space, and I gave you 5 vectors to play around with, right? Well, shoot, I could just choose one vector as the x-axis, vector 2 is the y-axis, vector 3 is the z-axis, and the extra 2 vectors are just extra redundant, a waste of stuff, right? It's not the extra 2 vectors aren't going to give you any more in this 3 space, but they're not taking anything away. And just from the first 3 vectors alone, we are going to be able to span all of R3. The extra 2 vectors are just extra fluff, basically. Does that make sense?
Yeah.
Okay, so that actually segues really well into problem 4. That wasn't completely intentional, but they're basically asking us that V1, V2, and V3 are dependent with each other in R7. And now they're saying, okay, let's add 2 more vectors, V4 and V5. And they're asking you, is V1, V2, V3, V4, V5? Is this linearly dependent or not? What do you think?
Not all of it as a whole, right? Only V1, 2, and 3 are dependent.
Yes, but hang on. What's the definition of linear dependence or independence?
It's like one answer determines the other one.
Right.
Right.
Let's be. That's intuitively that's correct. But let's use a very cut and dry mathematical definition, right? The definition of linear dependence in R7 means that there exists in A times V1 plus B times V2 plus C times V3 equals 0. So there exists a non-trivial A, B, and C, right? That's explicitly the definition of linear dependence, if I'm not mistaken. Let me double check that real quick. I just want to get it very carefully correct. So right, a non-trivial linear combination of the vectors that equals the 0 vector, right?
Wait, really quick. I think I've asked you before, but I don't remember. What's triviality? Trivial?
Yeah, no worries. It's a question that it's something that pops up over and over again, and you want to get it rock solid as you go through the course. But trivial, the trivial solution is one where A is equal to 0, B is equal to 0, and C is equal to 0, right? If this is true, then obviously 0 plus 0 plus 0 is equal to 0. So we call this selection of A, B, and C the trivial solution, right? Any other A, B, and C where at least one is non-zero is considered non-trivial. And what that means in practice is that, like negative V1 plus like 2V2 minus 3V3 or some combination of them happens to land you right back at the origin, right? What that's saying is sort of like, okay, you ride V1 down this far, then you ride V2, then you ride V3, and then you end back at the origin. That's what it means by non-trivial. Whereas trivial means that if they're all 0, then you just never left the origin in the first place, and that's not interesting. Do you kind of like pictorially see that?
Yeah. So
Yeah,
recap: trivial is you never really moved from that one point you were at.
exactly.
Non-trivial is there's a path that the vectors can take that lead back to the origin.
Exactly, yeah. That's a good visual way to think about it if you want. Yeah, like using V1, V2, and V3, and you're allowed to stretch, shrink, or reflect them, you can add them up in some way that gets you right back to the origin.
Gotcha.
That's what a non-trivial solution is. There might be like a weird edge case if V2 and V3 are themselves 0. Uh, anyways, I don't want to talk about a weird edge case like that right now. I think that would only serve to confuse. Yeah. But this is the fundamentals, right? This is trivial when they're all 0, and non-trivial is anything other than that. So what they're telling you is that you have a non-trivial solution, non-trivial linear combination of V1, V2, and V3 that adds up to 0. Okay? So that's like literally some value of A, B, and C. It could be like 1.1 or 2.7 or 3.5, like some, honest to goodness set of A, B, and C, right? Some real values. This is just something I pulled randomly, right? I'm just as an example. But like literally for some A, B, and C, this adds up to 0. So now they're asking you, okay, you added 2 more vectors into the mix. Does there exist some? So I'm gonna be very careful here. Okay, v2 plus v3. How do I want to do this? Um, what I'm going to use. Uh, sorry, I'm trying not to give away the answer, right? Um, so each of these is going to have a coefficient, and let's call each of those coefficients like z1, z2, z3, z4, and z5. All right. So basically, I'm asking you, does there exist a set of real numbers z1, z2, z3, z4, and z5 that gets this entire thing to add up to 0, other than the case where they're all equal to 0? So I don't care about the case where all of these are equal to 0. Like, that's obviously going to work. I don't care about this case. I want to find a non-trivial case. Can you find me a non-trivial case to get these to add up to 0? Given that this is true, can you reuse this fact somehow?
Yeah, can't you just plug in A, B, and C for Z1, 2, and 3, etc.?
Yeah, that's off to a great start. And then what about Z4 and Z5?
Can't you just make up one that would work?
You're not necessarily guaranteed. You got to be a little bit more specific. I don't have a guarantee that.
Yes.
What's up?
Oh, yeah, you're right. Because there's no
Yeah,
guarantee that if I plugged in D and E that it's going to equal 0.
right. But you're off to a great start, right? A, B, and C as Z1, Z2, and Z3 is exactly along the right tracks, right? Let's just see if we can find some other way to make these two values 0. Right? If this part was already guaranteed to be 0, and this part is 0,
Well,
what's up?
you could subtract to the other side, right? So that you can make Z4 V4 plus Z5 V5 equal to the
You're just
other
doing
side.
some gymnastics here.
Oh, okay.
Can you propose me some honest to goodness values for Z4 and Z5 that will guarantee these two will be 0?
No.
What's the simplest thing? What's the simplest? If I just asked you, devoid of all context, to guarantee me that this sum is 0, and I say you're allowed to choose Z4 and Z5, what would you tell me?
I would say 0, but you said
Exactly.
you
Well,
can't.
hold on. 0 is exactly right. 0 is exactly right. And you might be worried, but like, hey, I thought we said that we're not allowed to have trivial solutions, right? That's probably what you're thinking.
Yeah.
A trivial solution is when they are all 0. Trivial
Yeah,
solution
you're
is when
right.
they're all 0. If you give me 1 or 2 zeros and the rest are non-zero, that's non-trivial. That's perfectly fine. That's what I'm looking for, right? The problem guaranteed us that not there exists some A, B, and C non-trivial, such that this is true. And then you plug them in over here, so still we have the guarantee that Z1, Z2, and Z3 are not all 0. It's okay if Z4 and Z5 are 0, because we know that some of these are non-zero. You see that?
Yeah.
Yeah, so get that definition of trivial. Think about that definition of trivial very carefully, because that's. I feel like this is something that probably trips up everybody once when they learn linear algebra. Is that trivial means, sorry, non-trivial means not all 0, but some zeros are okay, just not all zeros, right?
Gotcha.
Trivial is when all zi are 0, and non-trivial is literally just putting a logical not in front of this. So non-trivial means not all zi are a zero. Some being zero are okay, as long as it's not all.
Gotcha.
Yeah. But yeah, you are definitely thinking along the right tracks when I like that you instantly saw that you could just reuse this, right? You were, that's sort of what this problem is sort of saying is that remember this interpretation of a non-trivial solution means that we can sort of like uh, walk around in like a kind of cycle almost, end back at the origin.
Yeah.
Well, let's say that let's say that this was some multiple. Let's say that this one was A v1, and this one was B v2, and this one was C v3, right? So in this combination, you can end up back at the origin. And now I'm saying, okay, I've given you these extra two tools in your toolbox, v4 and v5, to help you end up back at the origin. But it's like, wait, I already have a perfectly good path here that'll walk around and get me back at the origin. Why do I even need to use v4 and v5? I'm not even going to use them. And not using them is basically the equivalent of putting a zero in front of them,
Gotcha.
right? So hopefully that is sort of making it all connect.
Yeah.
Yeah. Okay. All right. Well, there was one more, but what's the last one? Uh,
Say just I think it's solved for A basically.
okay. Is this one very interesting or nah? It's
Other people were asking about it, but I kind of got it. So it's up to you if you want to do it.
I haven't actually looked at this one yet, so maybe I'll just quickly sketch it out. But yeah, I hope this discussion is generally making you feel a bit better about some of these concepts. Uh, some linear algebra classes you can get away without like thinking about what's actually happening with these vectors. Like sometimes linear algebra classes are just these super grindy computational classes, and those classes tend to be easy. But I feel like students are like, yeah, I didn't learn anything at all in my computational linear algebra class. So whenever I try to teach someone linear algebra, I try to get them thinking about like what's happening with one of these non-trivial solutions, rather than just grinding out another RREF calculation. But okay, so it's basically asking a range of values of A so that V1, V2, and V3 are linearly independent, right? Which basically means that if we put them inside a matrix, 4, 5, 6, and A10, right? And I guess we can augment it with 0, 0, 0, but it doesn't really matter. We're basically just doing a RREF here. Um, and we're going to find that we're going to be able to get a pivot point for this variable, no problem, right? After we do some calculations. But then with this one, A needs to be a specific value in order for there to be a leading a leading one or a pivot point in the third column. Does that sound about right? Or rather, A
Yeah.
can't be a specific value. If A is some particular value, it fails, and I think everything else probably succeeds, is my guess. But I haven't done the calculation myself. Does that sound about right?
That's kind of what I got. I mean, you end up getting like a really nice reduced matrix, so it all kind of works
Okay.
out.
All right. Maybe it's not a single point. Maybe there's like a range of values that works. But yeah, it's something like that, right? But yeah, I think the point is had. You just want to turn this into a nice, beautiful matrix that looks something like this. But for some values of
Yeah,
A,
that's what
this
it
will
turns
mess
out.
up. Yeah. But for some values of A, this will get messed up because one of the columns or rows will be zeroed out for a bad value of A. And you just got to figure out what that bad value is. But yeah, I think that's that. Anything else you want to discuss?
I think that's pretty much it. Wait,
Any other conceptual questions?
so
Or
my matrix at the end looks like that, right? The 1 1 1. That's literally what it is.
mm, yeah, I guess so.
There's like no A at the end.
Okay.
So
What does that mean? Like,
that
does your
that
A
means
just
that,
disappear?
yeah. Does that mean that all A's work?
Hmm, if you did everything correctly, hmm, I, I'm suspicious. Maybe I'll work this one out. Um, I would be your A can kind of disappear depending on what you mean, but I would suspect that not every value of A would work here. So how about I just quickly do this one? So I'll take the second row and subtract out twice the first. Oh god, that's going to be a pain in the butt. How do I want to do this? I hate calculations.
I did the same thing. It ends up being 1 4a, and then 0 negative 3 1 minus 2a,
Mm-hmm.
then 3 6 0.
6 0.
Sorry, I'm reading them all off my rows. Yeah.
Sure. Yep. Sure. Okay. And then what's the next
And
one?
then I did r or row 3 minus 3 times the first row,
Mm-hmm. So what did
and
you
that
get?
got me to 1 4. Yeah, that. And then 0 1 2a minus, or minus 1 over 3.
Sorry, say
And
that again.
then 0 negative 6 negative 3a.
Uh,
That second row is oh, that's the same thing, I think. Negative 2a. I got 2a minus 1 over 3. Is that the same?
it looks like you just took this and divided it by. Yeah, that should be fine. So 1 and then 2a minus 1 over 3. And then the last one you said was 6 minus. You said negative 6, right? And then negative 3a.
Yeah. Yeah.
Okay. And then I'll propagate this just a little further to see what we got here.
And then
So we can probably just
you
rewrite
go.
this. What's up?
Sorry.
Let's just rewrite this as, I don't know, what's the easiest? Divide this by 3, negative 3. So then this turns into a 2, and this just turns into an A, I think. Right? And then you can subtract out, you can subtract out that second row from each of the others. So then the third row becomes 0, 0, A minus 4A minus 2 over 3. 0, 1, 2A minus 1 over 3. And then 1 and 0 minus 4. God, I hate math, or I hate computation. A minus 8A minus 4 over 3. And then we basically just got to figure out how to get rid of the rest. Sorry, I realize that like grindy computations like this are a bit hard to follow along, so I'm just going to quickly try to crank it out. And
Yeah, you do.
yeah, so this is 3 over 3. So what does this look like? 1, 0, 0, 1, 0, 0. So that's A minus 8 over 3, which is minus 5A over 3 plus 4 thirds, 2A minus 1 over 3, and 3A minus 4A is minus A plus 2 thirds. This starting to seem like does this start to seem right? This is awful. So yeah, what I'm getting at this point is basically for any value of A other than A is equal to 2, this looks like it's going to work out okay. Does that seem right?
Think so.
Because for if this is equal to 2, if A is equal to 2, then this thing is equal to 0, which screws you over because then you lose that pivot point. But for any value of A not equal to 2, then you're golden. That's what it looks like to me. As always, check your math carefully and all, but I think that's what I got. Yeah. Any value of A other than 2, well, then you can just divide. Then you can just like normalize this row to be equal to 1, and then just cross out these rows as well, right? Or just zero out those values. But it all hinges on
Yeah.
this row, this value not being 0. This value needs to be non-zero. So yeah, I think that's what it is. Just be very sure to check your computations and make sure that make sure that I did my math right.
So then linear independent, it would be a non-trivial or trivial? The
Linear
trivial
independence.
zero.
Sure, I'll write it down. So linear independence is the same thing as uh, no non-trivial solutions. Linear independence means that there's no non-trivial solutions. Um, do you want me to like maybe just visualize this a little bit? Um, in sort of layman's terms, linear independence. Let's talk about R3, right? If you have three vectors in R3, like let's say the x, y, and z say the x, y, and z vectors, right? Like v1 is just the x, like say the unit vector in the x direction. Let's say v2 is the same for y and v3 is the same for z, right? Linear independence means that there's no there's no way you can draw a path. You remember before how we were talking about you could draw a path that gets back to 0, right? No such path exists with these three vectors. Do you see that? Other than just
Yeah.
making them all 0 to begin with. You can't, like, if I go out here, right, v2 and v3 aren't able to impact the value of the x-axis, right? If v1, if I write out, like, in the x-axis with v1, v2 and v3 isn't going to be able to get that x component back to 0, right? That's sort of the idea of there's no non-trivial solution here. Now, the concept, this was a kind of easy to visualize one because v1, v2, and v3 happen to also be orthogonal. But you can still have linear independence without orthogonality, right? You could have like, v1 and v2 be in the xy plane, but just not quite at 90 degrees. And then you could have v3 be the z-axis. And this one's a little bit harder to see, but you should still be able to convince yourself that you should still be able to convince yourself that there's no like path you can draw me with these three vectors that's going to get you back to 0.
Yeah.
Do you remember that?
Yeah.
Yeah. But like now, let's say that instead of the third vector being the z-axis, now let's say my third vector still exists somewhere in the xy plane. And now we have a bit of redundancy, right? We could write out a bit with this vector, and then we could like take the negative version of this vector to write over here, and then we could take the negative version of this vector to write back. You see what I mean?
Yeah.
Yeah. So hopefully that sort of, hopefully that sort of builds up your visual intuition for what independence or non-independence means. Hope that helped.
Yeah. It actually did a lot. Thank you.
Yeah, awesome. Okay. Yeah, so linear independence, no non-trivial solutions. I guess for this heck of it, I'll write, also like what exactly is the criteria? For a square matrix and by n matrix, uh there are going to be n pivots points. But yeah, I'm sure that this is basically one of those theorems in your textbook, right? I'm just sort of reiterating it now in the context of these visuals, and hopefully that maybe gets something to click in the brain. But yeah, I wish you best of luck, and I think any other questions for me? Any other?
I think I'm good.
Okay, all right. Best of luck. I'm gonna stop recording.